Hey, hello everyone. Welcome to our channel Physics, where we actually learn physics. So, in this lecture, we are gonna see a very interesting topic called as the plane angle. Okay? Not only this, we are also gonna see the different units of measurements for the plane angle. Like over here, you can see degree and radians. Okay, I have already talked about what is a radian in my previous lectures. Okay, so you can watch that also. But over here in this lecture, we are gonna talk about degree and radian in details, as much details as possible. Okay, so over here we are actually gonna understand what exactly is degree. Okay, what are the subtypes over there again, and what exactly is a radian. Okay, so all these things we are gonna discuss in this lecture itself. Okay, so this is going to be a fun, this is going to be a so much informative lecture about degree and radians. Okay, so I hope you will like it. Okay, so let's start with our lecture on the plane angle and degree and radians. Okay, so let's start. So first of all, I am going to talk about what is a plane angle. Okay, what is a plane angle? So first of all, let me make some space for plane angle. Okay, so first I am talking about this plane angle. Let's say over here. Okay, so first I'm going to define what is a plane angle and how do we actually define it, how do we actually represent this plane angle. Okay, so it's very simple. See, suppose we have this small line. Okay, suppose we have this small line, let's call this line AB with some length L. Let's say we have a line AB with length L. Now consider this point. Okay, let's consider this point. Let's call this point O. Okay, let's call this point O. Now if I join these 2 points, let's say I join AO and BO. Okay, so what I'm doing is there is a line AB and I am joining the edges, okay, edges of this line with the chosen point. Okay, something like this. Okay, something like that. Okay, same here with the point B. Okay, so what I have done here is I have joined AO and BO over here. Now you can see here that this line is subtending certain angle at this point, isn't it? There is a certain angle subtended by this line at a chosen point O. Okay, so we will denote this angle by theta. Okay, we will denote this angle by theta. So over here, this angle theta, okay, this angle theta is called as the plane angle. Okay, this is called as the plane angle. So how you can define it is very simple. The angle subtended by any line, okay, the angle subtended by any line with any chosen point. Okay, the angle subtended by any line at a chosen point, at a given point, is called as the plane angle. Okay, the plane angle. Angle subtended by any line, just highlight this word line. Okay, remember this. The angle subtended by any line with a given point is called as a plane angle. This is very important. Line. Okay, there must be some line and that line must subtend certain angle with any given point, and that angle at that point is called as a plane angle. Okay, for example, I can choose the same line over here, but now if I choose the point over here, okay, same line AB I'm saying, okay, let's say same angle, sorry, same line with same length. Now the point has just shifted, okay, like this. You can see now this line subtends again some angle, isn't it? It subtends some angle here. Okay, so this angle is also what? This angle is also what? A plane angle. This angle is also a plane angle. Okay, so you can see here this angle is definitely going to be a larger one because it is closer, so this is more open, isn't it? So you can see here that this angle is going to be larger than this one. And even if you can see, if you go even further, okay, if you increase this distance, this angle decreases, isn't it? This angle decreases, isn't it? So you can see here there is a relation, isn't it? There is a relation between this angle and this distance, isn't it? There is a relation between this distance and this angle. You can see as this distance increases, this angle decreases for the same length of the line. Okay, as this distance decreases, the angle increases. So you can see here there is a relation between the two, and we can see here that distance and the angle, they are inversely proportional, isn't it? We can check here. If I say this is distance r, let's say this distance is r, for example. So we can see here that this theta is somehow, okay, related to this angle. Okay, so this theta is related to this r, okay, by this relation, somewhat like this. Okay, now not only this, you can check one more thing. See, suppose now I take, let's say, same line, but now I increase the length. Okay, now I increase the length. Let's say length is now L dash. Okay, we have the same line, but the length has been increased. Now I choose the same distance as here. Okay, I'm choosing a same distance, you can see. Okay, same distance r, okay, here. And now you can check. You can check here. We have the same kind of a diagram. Only thing is this line had a small length, this line has a large length, and in this case you can see here, you can observe that this angle is greater. Okay, this angle is greater. That means what? That the angle depends on the length of this line also. Okay, the angle depends on the length of this line also, isn't it? More this length, more is the angle, isn't it? So that means we can see here that theta is directly proportional to the length, whatever is the length. You can check here. You know, if you make this length smaller, the angle is going to get smaller. If you increase it, okay, if you increase it more and more, what will happen? The angle will increase, isn't it? Okay, I'm talking about the same length, huh? This length should be same, and if you increase this length, okay, what will happen? This angle will increase. So you have two relations. One says that theta is inversely proportional to this distance, and this relation says that theta is directly proportional to this length of the line. So from this we can say that theta, okay, that theta is equal to L upon R. Theta is equal to L upon R. So that's how actually we have defined, okay, that's how we have defined theta. Theta is equal to the ratio of length of the line to the distance from the line to the given point at which the angle is subtended. Okay, at which the angle is subtended. Okay, so this is how we define it. So now we don't require much more of these diagrams. Okay, for our purpose in this lecture we just require that equation. So I'm just going to wipe it out. Okay, and I'm just going to write this equation over here. Okay, right here. So this equation is theta is equal to L upon R. That's it. This is what we require. Okay, so this is how you can remember about the plane angles. Okay, about the plane angle. So here, just revising this, what is a plane angle? The angle subtended by any line, okay, angle subtended by any line at a given point is called as a plane angle, and it is defined by this equation. Okay, and how we got to this equation? It was very simple. Theta depends directly on this L. We can see more this length, more is this theta. And we also saw it depends on this r also, it depends on this distance also. We saw here, as we increase the distance, theta decreases. As we decrease the distance, theta increases. Okay, so it is inversely proportional. So in this way we have defined theta. Okay, so this is the conventional way of writing the equation for theta, the plane angle. Okay, and over here, if this length is in meters, okay, if this length is in meter and r is also in meter, okay, then theta is in radian. Okay, remember this. Okay, so over here, if length is in meter, r is in meter, then theta is going to be in radian. Remember, this meter and this radian, they are both SI units. Okay, so over here I can just say these are what? SI units. Okay, so the theta that you get when you divide these two, okay, that is in radian. Okay, you can't put any number over here in centimeter or millimeter, you just have to put in meters. Okay, then only you will get in radians, otherwise there is no other way. Okay, so this is how we get the radian. Okay, this is how we get the angle in radian, and this is how we define the plane angle. Okay, now we will move and we will see what is a degree and how do we actually define a degree. Okay, as I said that angles are actually measured in degree as well as radian, right? Radian is a SI unit, but as we all know, generally we don't measure any angles in radian. We first measure the angles in degrees. Okay, we first measure the angles in degrees only. Okay, then we convert it to radian. So over here in this lecture we are gonna see what are the conversion factors, what are the links, what are the relations between degree and radians. Okay, so all these things are coming up. Okay, at the end of this lecture we are going to see the conversion factor between these two. First of all, we will understand what is a degree and a radian. Okay, what is exactly it is and how do we got to these radians, etc. Okay, all this. So first of all, I'm going to start with degree. What is a degree? Okay, now imagine this circle over here that you can see. Okay, now let's say this is the center of this circle, for example. Okay, I think it should be shifted a little bit. Okay, let's say here it is. Okay, let's say here is the center of this circle. Now what you do is choose any arc. Okay, let's say I choose this arc over here. Okay, for example, I choose a arc on this whole circumference of the circle. Okay, I have chosen what? A small arc on this whole circumference of this circle. Okay, now you can see here that this circumference, this arc has got certain length. Let's say it is having a length of L, for example. Okay, let's say this is having a length of L. Okay, now you can see here, just like over here, just like this line subtends certain angle at this point, similarly this arc that we have chosen will also subtend certain angle, isn't it, with this center of the circle. You can see here the arc is subtending certain angle. Let's call this angle theta, isn't it? Let's call this angle as theta. Okay, now, so I hope this is clear. This arc that we have chosen is subtending certain angle at this center. Okay, now in this way I can choose any arc, like I can choose an arc as big as this. Okay, I can choose an arc as big as this. For example, I have chosen this arc. Let's say, let's remove this one. Okay, now you can see that this bigger arc, okay, let's say it has a length of L, for example. Okay, and now you can see this arc is subtending certain angle theta, okay, with the center. Okay, let's call this angle theta. Okay, so now I hope you have got this idea how any arc on a circle is subtending certain angle. Okay, now imagine that we have divided, okay, imagine that we have divided this whole periphery of this circle, or we have divided this whole circumference of the circle into exactly 360 parts. Okay, exactly 360 parts. Okay, just imagine that we have divided this into exactly 360 parts. Now just imagine how small each part is going to be. Okay, in case of at least our circle. Okay, in case of this circle, each part would be very small, like this. Okay, it should be like this, even smaller than this. Okay, because I am not able to draw that small part over here. Okay, you can see here that if I divide this whole circle into exactly 360 part, then each small arc is going to be very small. You know, just like we drew those arcs. Same here, you will have very small arcs over here, isn't it? Each arc will be of exactly same size, because same length, because we have divided the whole circumference into exactly 360 equal parts. So each arc now which is formed, okay, each arc now which is formed, okay, will be very small and will be of equal size, equal length. Okay, now let's assume one of such small arc. For example, I choose this one right here. Okay, I choose these 2 points. For example, see, basically when we divide into 360 part for this circle, each part is going to be very small. Okay, it is going to be very small, but for a representation purpose I have shown you a little bit bigger one. Okay, so let's talk about this small arc over here. Now just like we saw, every arc subtends certain angle with the center, isn't it? With the center. So this arc is also going to subtend certain angle, isn't it? You can see here, this small arc is also subtending certain angle at the center, isn't it? In fact, if I choose any other arc over here, this arc also is going to subtend certain angle at the center. Okay, or I can choose any other small arc, okay, after dividing into 360 parts, right? So we can do that, and you can see here, each small arc is subtending certain angle theta. Okay, now this angle, okay, this angle subtended by this arc, by this small arc, is called as 1 degree exactly. Okay, this is called as exactly 1 degree. So now you might be getting a little bit of idea how exactly do we define 1 degree. Okay, so it's very simple. See, you have a whole circle, right? You have a whole circle. The circle has a whole circumference or a periphery. What you have done is you have divided the periphery, okay, you have divided this circumference into exactly 360 equal parts. Okay, so that means now there are exactly 360 small arcs, okay, on this circumference of the circle. Okay, there are 360 equal arcs on the circumference of the circle. Each arc is subtending certain angle with the center, and that angle is called as 1 degree. Okay, that angle is called as what? 1 degree. Okay, so now I hope you have got this idea about how exactly do we define 1 degree. Okay, how exactly do we define 1 degree? Yeah, you might just ask, why exactly 360 parts? Okay, you might just say, why exactly 360 parts only? Why not 500? Why not 1000? Why not 2000? Why not 10,000? Why not 100? Why not 10? Okay, so that is a question to all, but basically this is what we have chosen. Okay, this is the conventionally chosen number historically. I mean, maybe there may be some historical reasons behind this number. Yes, we could have chosen 500, we could have chosen 1000 also. Any number could have been okay, no problems, okay, at all. But we have chosen this, and now we have to deal with this only. Okay, we have to deal with this only. Okay, even if we would have chosen 500, that would have still worked up, no problems at all, definitely. Okay, no problems. Okay, because you are going to see there is one thing, okay, that is coming up. There is one thing related to any circle that is constant. Okay, whatever number you choose, whatever times you divide it, it doesn't matter, but there is one thing with a circle that always remains constant. Whatever is the size of the circle, okay, big or small, whatever, but there is a one constant thing, okay, which is always same, okay, for any kind of a circle, any bigger, smaller, that number will always be there. Okay, so that's why it is not gonna matter. So this 360 is not, definitely should not be a question for us. Okay, yes, this is historically chosen, so we have to deal with it. Now since we have said here that each small section is subtending an angle of 1 degree, okay, at least this is how we have defined it. So that means, see here, there are 360 exact parts. Each part is subtending 1 degree. So how much is going to be the total angle subtended by this circle? Definitely it would be 360. Okay, so if I just find out this total angle, okay, this total angle subtended by the whole circumference of this circle at its center is going to be 360 degree exactly. Okay, so this is how we define a degree. Okay, this is how we define a degree. Now we are going to go even further. Okay, we are going to go even further. Okay, see, this is a small angle 1 degree, but there are cases when we deal with even smaller angles than 1 degree. Okay, there are cases where we deal with angles which are even smaller than 1 degree. So now we have to see another scale of angle, plane angles, okay, which is even smaller than 1 degree. Okay, just like, for example, you have that meter scale. Okay, you have the meter scale, Okay, on the meter scale, you see there are markings, 100 markings. If you take a 1 meter scale, okay, 1 meter is equal to 100 centimeter, we all know. Okay, so there will be 100 such markings, okay, each of 1 centimeter, okay, each of 1 centimeter length. So there will be 100 such marks. Okay, so we can see here that 1 meter is further divided into 100 parts. But as we go deep in, okay, as we go deep in, we will find that each centimeter, okay, each centimeter is again divided. See here, if I zoom this up picture, if I zoom this 1 centimeter, then you will find out that 1 centimeter is again divided into 10 parts. Okay, it is again divided into 10 more parts, something like this. Okay, and each part is called as a mm. Okay, 1 millimeter. So you can see that there is a scale within another scale. Okay, you can see there is a scale within another scale. So same here we have to do. This is right now the smallest angle, okay, on our scales right now. Okay, on the degree scale, 1 degree is going to be the smallest angle, but we deal with even smaller angles. So we require another scale which gives us values of the plane angles even smaller than 1 degree. Okay, so that means we need another scale within 1 degree. Okay, so what I will do is I will just zoom this picture up. Let's say this is 1 degree. For example, see, I have just chosen this small section over here. Okay, let's say this is our center and this is the arc that is here. Okay, okay, now let's say this is 1 degree. Okay, Let's say this is 1 degree exactly. Okay, now we need another scale, right? We need another scale. So what we do is now we divide this 1 degree into 60 exact parts, 60 exactly equal parts like this. Okay, we divide this 1 degree, okay, this, or you can say the arc associated with 1 degree is now divided into 60 equal parts. Now you can see again over here there are even smaller arcs. You can see here there are even smaller arc. Okay, now again you will find out that each of these arcs is going to subtend certain angle at the center, right? Somewhat like this. Okay, it is going to subtend certain angle at the center. If I choose any arc, okay, see, this is a 1 degree and this same picture has been drawn here by just magnifying it. And now what we are doing is this small arc which is magnified here is again divided into 60 equal parts. Okay, and again you will have 60 very small arcs. Okay, now you can see here each small arc is going to subtend certain angle at the center. Okay, and this angle, okay, and this angle subtended by this small arc at the center is called as 1 minute. This is called as 1 minute. Okay, so this small angle over here, okay, over here, this is called as 1 minute, and this is how we denote it. Okay, 1 minute. Okay, this is how we denote it, 1 minute. Okay, so I hope you got this idea how exactly we have defined 1 minute. Okay, we started with this whole circle. Circle had a whole circumference. We divided the circumference into exactly 360 equal part, and we chose one small arc. Okay, one part in 360 parts of the whole circumference, and we saw that this one part subtends certain angle at the center, and that angle is defined as 1 degree. Total angle would be how much? 360 degree. Now we chose this 1 degree over here, just took this part and just magnified here and shown you over here, right? Now what we did is we again divided this small arc, okay, over here. See, this is zoomed up. So this small arc is again divided into 60 equal parts. Again you can see now you have 60 smaller arcs. Okay, you have 60 smaller arcs. Again you can see each arc is subtending certain angle at the center. So that angle is called as 1 minute. So it's very simple. When the arc associated with 1 degree angle, okay, when the arc associated with 1 degree angle, okay, 1 degree angle is divided into 60 equal parts. Okay, when 1 degree or this arc associated with 1 degree is divided into 60 equal parts, okay, then each small arc subtends certain angle at the center. Okay, simply I can say when 1 degree is divided into 60 equal parts, then each part subtends certain angle at the center, and that is called as 1 minute, and this is how we define it. Okay, so I hope this is clear how we have defined 1 minute. Now there is a even bigger problem. I should say even smaller problem. Okay, actually in many cases we deal with even smaller angles than 1 minute. Okay, we deal with even smaller angles. Imagine that. Just imagine. Already we saw how small is 1 degree. Then further we divided 1 degree into 60 parts. Imagine how small this 1 minute would be. Okay, and now again we are saying that we require even smaller scales than 1 minute. That means there are cases where we actually encounter angles even smaller than this. Oh my God. You can imagine how small those angles would be, isn't it? We again require even smaller scales. Oh my God, you can just imagine. Okay, so in this case, now we again define another even smaller scale than 1 minute. That means within 1 minute, we require another scale, scale within scale. Okay, so what we do is again, see this part, this 1 minute part, I will just take it here down and I will just zoom this up for you. Okay, let's say this is exactly 1 minute. Let's say this angle is 1 minute, for example. Okay, now what we do is again we divide this arc associated with 1 minute into 60 parts. 1 2 3, like this, 60 equal parts. Okay, this is not 60 right now because I'm not able to draw. Okay, you will not be able to see them. So let's say these are 60 equal parts. Now you can see here again you have a very small arc. Okay, again you have a very small arc. Now this arc, okay, any arc you can choose, this arc is going to subtend certain angle at the center, right? At the center, something like this. Okay, somewhat like that. Okay, this angle, now this angle is called as 1 second. This is called as 1 second and we denote it like this, 1 second. Okay, so this is, I would write here 1 minute. Okay, this is 1 second. Okay, this is 1 second. So this is how we define it. Okay, so you can see 1 minute angle is again divided into 60 equal parts. Then each part corresponds to an angle of 1 second. Okay, see 1 minute. Okay, 1 minute angle is again divided into 60 equal parts. Okay, then each part subtends certain angle at the center and that angle is called as a 1 second. Same here, 1 degree is divided into 60 equal parts and each part, okay, subtends some angle at the center, that is called as 1 minute. Then again we divide 1 minute into 60 equal parts, each part subtends certain angle at the center and that is 1 second. Okay, okay, so you can just imagine how smaller these values are, how smaller these angles are, and how amazing, okay, how amazing these measurements would be when you will actually go to do this. How amazing this experiments would be when you are dealing with angles like seconds. Okay, you actually do deal with, if you are a scientist, if you go for research purpose, especially in astronomy, you actually deal with such small angles. Even in optics also, we deal with these angles, smaller angles. Okay, so you can imagine how small angles we have to deal with. Okay, so this is degree, this is minute, this is second. I hope this is clear, how we define 1 degree, how we define 1 minute, and how we define 1 second. One thing you can note, this is 1 degree and this is divided into 60 parts and you get one part as 1 minute. So that means 1 degree is equal to how much? 60 minutes. Okay, remember this. 1 degree is equal to how much? 60 minutes. And same here, you can see this is total angle is 1 minute and the 60th part of 1 minute is 1 second. So that means the total number of seconds in 1 minute would be how much? 60. So that means we can write over here, yeah, here I can write, okay, I will write it here, 1 minute is equal to 60 seconds. Okay, so you can remember these equations. Okay, so these are very important equations that we have just got. Okay, so I will just put these equations over here. Okay, so that this will be stored over here. Okay, now we can do the further job, that is radians. Now we have to define what is a radian. So I will just note down this main equation. 1 degree is 60 minutes and 1 minute is equal to 60 seconds. Okay, just let's keep these in mind. Okay, somewhat like this. Okay, so in this way degree has now been defined, degree, minute, second. Now we move to this radian part. Okay, so let's see what is this radian now. Okay, so now let's define what is a radian. Okay, so over here you can see a circle. Okay, before we exactly define what is radian, just let's see few terms that are going to be important. Okay, so you can see a circle over here. Okay, now what I'm going to do is I'm going to apply this definition to the circle. Okay, I'm going to apply this definition to the circle. Okay, and let's see what happens in this case. Okay, so first of all, let's see, let's say this is the radius. Okay, let's say the radius is r. Okay, radius is r. Okay, now here suppose I choose a small arc. Okay, suppose I choose a small arc. You can see from here to this point. Okay, I have chosen a small arc. Now you can see this arc subtends certain angle, isn't it? Let's call this angle theta 1. Okay, and let's call this length of the arc as C1. Okay, for some reasons I'm calling it C1, and let's call this angle theta 1, and this is again radius, right? Okay, so what I have done is I have chosen a small arc with length C1. Okay, and we can see this arc subtends certain angle at the center. Okay, at the center. Now using this definition over here, you can see there is a kind of a arc or line which subtains certain angle at a point theta, and it is defined as this length divided by this distance r. Same we can do here. Over here we have this point, we have this length of the arc, and this is the distance. So in this case we can say this theta 1 is equal to this length. Okay, you can see this length over here and this distance. Okay, so we can just write C1 upon r, right? So this would be our first formula. Okay, now we move on. Let's say we have increased the length of the arc. Okay, from here. Okay, let's say we have increased the length of the arc. Okay, let's say from here, and now you can see this arc subtends even bigger angle. Okay, let's call this angle as theta 2, and let's say this arc length is C2. Okay, let's say the arc length is C2. Okay, so you can see what we have done. We have chosen this bigger arc of the circle, and the length of the arc is C2. Okay, then with the center, this arc subtends an angle of theta 2. So again applying the same definition, so from this I can write theta 2 is going to be equal to C2 upon r, right? Okay, so we have got another formula. Now let's move on. Now what I will do is again I will increase the length of the arc. Okay, let's say now the arc has been increased. Let's say it is here, somewhere here. For example, let's say it is here. Now you can see the arc has a bigger length up to this point. Let's call this arc length C3, and let's say the angle subtended by this whole arc with the center is theta 3, for example. Okay, so again applying the same definition, we can say here theta 3 is equal to C3. Okay, C3 divided by r, right? This is r. Okay, so again we have another formula. Now what I will do is I will move even further. Let's say I move somewhere here. Okay, let's move from here to this point. Okay, okay, now you can see I have moved here, so that means now the arc length is even bigger. Okay, even bigger, and you can see now it traces even larger angle. Let's call this angle theta 4. Let's call this circumference, let's call this arc length as C4. Okay, so in this way you can see here the arc length has increased and the angle has also increased. So again applying the same definition, theta 4 would be equal to this arc length C4 divided by the radius r. Okay, radius or this distance. Okay, so in this way we have got these 4 formulas. Okay. Okay, now let's move to the last one. Okay, just check what I am telling here, because this is not really something that you should note. Just understand this. Okay, now we move even further. Let's say I move even further and I reach here itself. Okay, I reach here itself. That means I started from here, and now I am choosing the whole circle or the whole circumference, okay, as the whole arc. Okay, so that means now the arc length is nothing but the circumference. Okay, in this case the arc length is nothing but the circumference itself. Okay, so let's see what happens in such a case. Okay, now over here what I have done is we have chosen the whole circumference as the arc length, and now you can see it is tracing a total angle of a circle, isn't it? It is tracing a total angle of the circle. Let's call this arc length, total arc length, as C. Okay, because we know the total arc length of the total circle is nothing but the circumference. So let's call this C, and let's call this angle as theta. Total angle of the circle is, let's say, theta. Okay, or we can say the total angle subtended by this circumference with its center is called as theta, let's say. So again, applying the same definition, we can write here theta is equal to C upon R. Theta is equal to C upon R. Okay, so now we have got a very important, very interesting equation. Now we will just analyze what this equation is trying to say. Okay, and what people found out about this equation, and how exactly people came out with something new, something interesting. Okay, now this equation is very important historically also. Okay, because historically when people, I mean scientists, okay, when they did experiments with circles, not experiments really, but when they tested for various circles, various sizes of the circle, they found something very common. Okay, they found something very common. Okay, here you can see, look at this equation. Over here is a ratio of circumference to the radius. Circumference to the radius. Okay, this is the ratio. Now people did this. People actually did lot of analysis about this for various sizes of the circles, and they found out for every kind of a circle, for every size of the circle, the ratio circumference upon its radius is always a constant. Okay, the ratio is always a constant, and they found out that this ratio, that is C upon R, is always equal to some constant 2 pi. Okay, 2 pi. Now what is pi? Pi is a constant that these people found out, and to be equal to 22 by 7 or 3.14. Okay, see, this is a never ending number actually. Okay, it never ends, but we have taken it 3.14. Okay, so now this is what these people found out. Okay, this is what these people found out. Okay, whenever you divide the circumference with the radius of the circle, you always get this number. What? 2 pi. Okay, 2 pi, or 2 times 3.14, 2 times 22 by 7. That is what you get always. There has not been a single exception, single instance where we have not got this. Always you get the same number, that is 2 pi. Okay, so that was amazing, that was surprising for everyone, isn't it? People thought maybe sizes are different, so properties will also be different, but no, this was something that was common. Okay, so over here, now let's analyze this equation carefully. Now what is this? C is the circumference, or in a way I can say the total arc length, okay, of the circle. R is the radius, okay, R is the radius, and we can see here this total arc length is subtending an angle of theta. It is subtending an angle of theta with the center, isn't it? And we have written this equation here. Now historically we found out this equation always, okay, and if we compare now these two equations over here, we can write here that theta is equal to 2 pi, isn't it? Theta is equal to 2 pi, isn't it? Okay, that means what? That means the total angle subtended by this circumference of this circle with its center is how much? It is 2 pi. Okay, it is 2 pi. And look at this. This is what? It's like just this equation. Length upon this length. Okay, length upon that length. And you get this angle, isn't it? So same here. Length upon this length, you get this angle over here. Okay, and as I said here, if this is in meter, this is in meter, this theta is in radians. Okay, so over here, this theta that you got is in radian. This theta that you got, okay, that is also in radian. That means the angle that you get here is 2 pi radian. Okay, so whenever we say that the total angle of the circle is 2 pi, it's actually what we mean is radian. Okay, in radians, the total angle of the circle is 2 pi. Okay, it is 2 pi. Okay, so this is how this new concept or this new constant came into existence. Okay, this is how it came into existence. This is pi. Okay, and it's very important. You will see this term everywhere. Actually, you might have already seen this term many times in 10th or in 9th maybe. Okay, many times actually, but you may have not known exactly the story behind this, or may have not understood where do we get this value from. Okay, you know the constant value 3.14, but this is how we get it. This is what people did, and they always found out this ratio. You go and do the same experiment. You go and check. Okay, if you want to test, draw circles with any radius and find the ratio of circumference to the radius. You will always find out this constant. Okay, always. So that's pretty amazing. Okay, so in this way we have now this new definition that total angle of a circle is 2 pi radians. But now just recall, we have just talked about what is a degree. Okay, over there we defined 1 degree. And how did we define? By dividing the whole circumference into 360 equal parts. Over there we said that the total angle of the circle is how much? 360 degree. And over here we are saying the total angle of the circle is 2 pi radians. So we got some link over here between the radians and the degree, isn't it? Okay, you can see here there is some link. In radians it is 2 pi. Okay, in radians it is 2 pi, and in degrees the total angle is 360 degree. So that means we can say that 2 pi radian, okay, is equal to 360 degree, isn't it? So that's a very interesting, very important equation, very important relation between degree and radians. Okay, very important. From this we can also write, see, I can just put here pi radian, okay, and we can just divide this 2 on the other side, or I can say let's divide the whole equation by 2 on both sides. So in that case 360 divided by 2 is 180 degree. So now we have got another term. Pi radians is equal to 180 degree. Okay, pi radians is equal to 180 degree. Now, what do we really mean by this is very simple. See, from this equation I can show you what do we really mean by this equation. Take this equation. Now, what you do is divide this whole equation by 2 on both sides. So, it will be c by 2r, right? It would be c by 2r equal to pi, right? I have divided by 2 on both sides. I can also write this equation as c by 2 upon r is equal to pi. Now look at this equation. Okay, look at this equation. This is c by 2 upon r. Now what is c by 2? Half of the circumference. Okay, where is the half of the circumference? Let's go here and see. See, here is the half of the circumference, somewhere here. Okay, look at this arc length. Okay, this arc length. This is what? C by 2. Okay, this is our center, this is radius, this is radius. Now you can see this half circumference is subtending certain angle with the center. Okay, with this center over here. Okay, and that angle, let's say, is theta. Okay, for example, again using the same definition. So theta would be equal to what? The arc length, that is c by 2, divided by the radius, that is r. Okay, now compare these two equations, c by 2 upon r, c by 2 upon r. So if you compare, you will find out that theta is equal to pi. Okay, that means for half circle the angle is how much? Pi radians. Okay, for half circle the angle is how much? Pi radians. Okay, same is reflected in this equation also, you can see. Same is reflected in this. This is half circle, right? Total is 360. Half would be 180. And over here you can see it corresponds to pi radians. So half circle corresponds to an angle of pi radians. Okay. So now we have got certain values. Okay. Let's just recall everything that we have just seen. Okay, let's see what are the important values that we need to remember over here. Okay, so let's see what are the important relations that we have seen so far. Okay, so one of them would be definitely c by r is equal to 2 pi. Just now I talked about. Okay, also we talked about this relation that 2 pi is equal to 360 degree. Okay, this is in radians and that is in degree. Okay, same, then we found out pi is equal to 180 degree. Okay, again this is in radian. Okay, remember this. Okay, whenever you are writing this pi, okay, that is always in radians, remember that. Okay, now from this equation you can also see c is equal to 2 pi r, isn't it? And this is a familiar equation for you. Then you have seen this equation many times. In fact, you have used it a lot of times to find out the circumference of a circle, isn't it? Okay, so this equation comes out from here actually. This equation comes out from this equation itself, because this is a experimental equation. Okay, experimentally arrived at equation, and this is equation that we got from this equation. Okay, so these are some equations. Also at the same time we have got these equations also with us. Okay, so now we have quite a few equations with us. Now we can move on to the very important topic, that is the conversion factor between degree, minute, second and radians. Okay, conversion factor between degree, minute, second and radian. Okay, so let's see what is the conversion factor. Okay, so what we will do is we will actually convert, okay, 1 degree, okay, into radians, okay, 1 minute into radians, 1 second into radians, and we will do the vice versa also. Okay, so first of all, we need to remember this equation over here. Okay, for this conversion part we just need to remember one equation, this one, nothing else, that's it. See here, this is 180 degree equal to pi radians. What is pi? 3.14. So I will just write 180 degree is equal to 3.14 radian. Okay, now using this equation itself, we can just solve this. See here, I can write this equation as 180 times 1 degree, and that is equal to 3.14 radian, right? Okay, now we can also write this as 1 degree is equal to 3.14 divided by 180, and that is in radians, right? Okay, you can just understand this. Okay, now we can just calculate what this number is. I have this calci with me. I will just calculate for you. It is 3.14 divided by 180, and it is going to be equal to, yes, 3.14 divided by 180, and it is equal to this number 0.017444. Okay, I'm not going to write that in radians. Okay, so you have got this conversion factor. Okay, see, this is very important because we are gonna see a important method called as a parallax method, where we actually have to use these conversion factors. Okay, over there these conversion factors are very important. That's why we have to look at these numbers. Okay, so now let's move on. Now let's move and let's do the reverse. Okay, see, I can write this equation in this way also, 0.0174 into 1 radian, right? Okay, this is just 1, so it is not going to matter. So I can write this as 1 radian is equal to, I can take this term and divide this over here, 0.01744444, and let's see what answer do we get. Okay, yeah, it is, see, 1 radian after calculation, it comes out to be 57.32, okay, 48 and some number, okay, degree. Okay, so this is the conversion factor from radians to degree. 1 radian is this many degrees. Okay, so in this way we have done with the conversion factor from degree to radian. Now we move to this minute and second. Okay, minutes and second. So let's see what we can do. Okay, what I will do is I will use this equation right here, or yeah, this equation. Okay, this is 1 degree. Now you have just checked 1 degree is equal to how much over here? It is 60 minutes, right? So instead of 1 degree, I will write 60 minutes, and that is equal to this number, 3.14 upon 180. That is in radians. Now I can write this as 60 times 1 minute, and that is equal to 3.14 divided by 180 radian, right? I can also write this as 1 minute is equal to 3.14 divided by 180 times 60, right? Okay, that is in radians. So let's calculate what number we are gonna get from this. So it is 3.14 divided by 180 into 60. Okay, so over here the number that we get is something like just a minute, 180 into 60. Okay, I pressed some other numbers, I guess. Okay, so the number I get is this one. 1 degree is equal to 2.9074, okay, into 10 raised to minus 4 radian. Okay, 10 raised to minus 4 radian. Okay, so we have got this conversion factor. Okay, same thing we can do, okay, in the reverse order. That means we can find out 1 radian equal to how many, here it is seconds. I am sorry for that. Okay, sorry, minutes. It is minutes. Okay, okay, now we can do the reverse. Okay, I will do it here. Okay, see, this equation can be written as 1 minute is equal to 2.9074 into 10 raised to minus 4 into 1 radian, right? So we can also write this as 1 radian is equal to 1 minute divided by this number 2.9074 into 10 raised to minus 4, right? And we can just calculate this number and we will find out this as, yes, something like this. 1 radian is equal to, this number is 3439.49, okay, minutes. Okay, so this is the conversion factor. Okay, so in this way we have converted between radians and minute. Now we move to the next one, that is seconds. Okay, so let's see what is this second. Okay, so I will do it over here. Okay, somewhere here. Okay, now remember this, all these conversion factors are going to be very important when we will see numericals. Okay, numericals on the parallax method. Okay, parallax method we are going to just see in the coming videos. Okay, I think in the next video or maybe later than that we will see parallax method, and in that you will see that we are going to require all these quantities, that is minutes, seconds, especially minutes and seconds. They are very important over there. Okay, and believe me, parallax is a real method. It is used widely in astronomy. Okay, so over there people use it. Okay, see, degree, minute and second. Okay, these are the units of measurements that actually we have to use. Okay, we have, because our instruments are designed to measure these angles only, degree, minute and second. Okay, and while we are calculating, okay, when we are calculating, you know, the equation that we saw for the plane angle, over there when we have to put the angles, we have to put it in radians. Okay, so first of all we have to convert those degrees, minutes or seconds into radians. Then only we can use that value in our equations, because our equation only accepts SI units. That's why we are looking at these numbers. Okay, so now let's move on and let's see what is a conversion factor between second and radian. So what I will do is I will use this equation right here. Okay, yeah, this one, this right here. So you can see this is 1 minute, and 1 minute is equal to 3.14 divided by 180 into 60, right? That is in radians. Now 1 minute is equal to how much? It is 60 seconds, right? Just now we have seen. So this is equal to this much. Okay, now we can write this as 60 times 1 second equal to 3.14 divided by 180 into 60 radians. Now we can also write this as 1 second is equal to 3.14 whole divided by 180 into 60 into 60, right? That is in radian. Okay, just we have divided this 60 on the other side. Now let's see what answer we are gonna get from this. Okay, so it is 3.14 divided by 180 into 60 into 60, and the answer that we get is, yes, this one. 1 second is equal to 4.845 into 10 raised to minus 6 radians. Okay, so we have got this conversion factor. Now we can again do the reverse. Okay, 1 second is equal to 4.845 into 10 raised to minus 6 into 1 radian, and from this equation we can write 1 radian is equal to this number over here on the other side. Okay, 1 second divided by 4.845 into 10 raised to minus 6, right? Okay, so let's divide this and let's see what we get. So 1 divided by this whole number. Okay, and what we get is, it's a big number. 1 radian is equal to 206369.42, okay, seconds. Okay, so we have got this conversion factor again. Okay, so I hope this is clear. Okay, I hope I hope it is understood how we did this, how we converted, and most importantly, I hope that you understood what is a plane angle, what is a degree, minute, second, and what is a radian. How we got to this number, that is pi. Okay, how we got this formula, etc. Okay, so I hope everything is pretty clear to all of you. Okay, so I think that is it for right now. Okay, in the next videos we are going to talk about the parallax method actually. Okay, for now we will stop here. Okay, I will see you in the next video. Thank you so much for joining. Thank you so much for listening. Okay, have a nice day. Bye bye.